We're going to do oxymercuration-reduction. We have our alkene, the generic formula for the mechanism, and we're going to react it first with mercuric acetate in aqueous tetrahydrofuran, and secondly we're going to add sodium borohydride. Our acetate group looks like this. And the formal charge. Now, for the purposes of this mechanism, we don't really need to know what it looks like, but it's always good to remember that kind of things. So our product should look something like that, and let's see how that happens. We have our alkene, and then we have the mercuric acetate. It has two groups like this, and we gotta remember that Hg has a lone pair. So it's going to act as a nucleophile. It's going to attack this carbon right here. And then the double bond is going to attack it because it can also work as an electrophile. And while that happens, this OAC group leaves with the electrons from this bond. Then what we get is a cyclic structure like this, where the Hg is bonded to both carbons, and then it has this acetate group that it did not leave. It has a positive formal charge. Then this is the second step, and what happens is that water is going to attack the carbon, and the bond from the Hg and the carbon is going to break. The Hg is going to take the electrons, and it's going to take care of this positive charge. So in here, we see the product, it doesn't have the positive charge. But water, the protonated alcohol that we formed, it does have a positive formal charge right there. Then we copied whatever was there, we copied it here. And another water molecule is going to come into the picture. It's going to take this acidic proton, and the electrons are going to go back to oxygen to stabilize the positive charge. So we're going to get our hydroxyl group, which is the important part of it. Now we need to get rid of this group, this bulky group right there. We don't have it in our product. So what we're going to do is, this is the second part of the mechanism. This is when we add the NABH4. And what happens is that we don't really understand this mechanism up till now. They're still working on figuring out. But this is the reduction part. And what you need to know is that this group is always going to reduce. So what's going to do is going to add hydrogens to your final product. So we see it has the two hydrogens right here, and it looks just like that. Let me give you an example of that. So we have this molecule, it's an alkene obviously, and then we're going to react it with AgOAC2 and in the presence of H2OTHF. So let's do that. We have our alkene plus we have the Hg, we have an OAC up here and an OAC up here. And then what's going to happen is that the lone pair is going to attack as a nucleophile this carbon right here, while it's acting as an electrophile at the same time, and the double bond is attacking the Hg, and then one of the AC groups is going to take the electrons and leave. So the product of this would look like our cyclohexane with a cyclic structure with the Ag with a plus and then OAC. Then we're bringing the water. We copy what we have on that side, HG, really unstable, and then OAC. And then we add the water, H2O. And what's going to happen here is that the partial negative of the water is going to attack this partial positive carbon like this. And then this bond is going to break, and Hg is going to take the electrons to stabilize the charge. So now we're going to get our cyclohexane with the Hg here and the OAC group. And then on this carbon, we're going to have an O with two H's with a positive formal charge. Now, we copy whatever is there. And we have the mercury acetate here, OAC, and then we have our protonated alcohol with a formal charge of plus, and then another water molecule is going to come and is going to attack this acidic proton, and the proton is going to leave the electrons for the oxygen to stabilize the charge, and our product will be the Hg here, OAC, and then here our OH. Now we know we're getting close to this, but we're going to get rid of this big group. The way we do that is we bring in the NABH4, and we don't really understand the mechanism behind it. So luckily for you, you don't have to memorize it. And then we have the OH here. So we just know that by adding this, we just know that we are going to grab this big bulky group, and instead of that, we're going to add a hydrogen here. So our answer would be that, which would be the same as this, just grabbing the molecule and putting it that way. Let's see another example. We have our alkene, and we have the mixture, and we should expect that. Now let's check out the mechanism for this. We copy this structure. CH double bond CH2, and we know that this adds to Ag OAC, another OAC group here. And we know that this is going to act as a nucleophile, and is going to attack this carbon right here. And it also acts as an electrophile, so the double bond attacks it. And then one of the OAC groups leaves, like that. So our product is and then we have a cyclic structure right here with the Ag, formal charge plus, and OAC. Like that. Now we're going to copy whatever is on that side. We're going to copy it here. And then CH bond CH2. And now we know that we have the cyclic structure right here with mercury and the OAC up here. Now we know that water in the presence of tetrahydrofuran comes into play. So we're going to draw the water molecule. And we know that this is a polar molecule and the oxygen is partially positive. Now let's think of which one of these two carbons it's going to attack, because it can attack either one. Now, the more stable one is going to be our major product. So if we attack this carbon right here, then it's going to have 1, 2, 3, 4, 5 bonds. So in the transition state, it would be partially positive. As if we attack this other carbon right here, then this carbon would be the partially positive one with 1, 2, 3, 4, 5 bonds. So in stability of carbocations, we learned that secondary is better than primary. So we work the same way with partial charges. The more stable one is going to be the secondary instead of the primary. So this water mostly is going to attack this carbon right here. And our product should look like and instead of the ring, this side of the bond is going to break and is going to take the electrons. So the Hg, we expected to see it here. And then the protonated alcohol group, we expected to see it here with a positive formal charge. So I'm going to copy whatever is on that side to this one. And we know that the Hg is here with OAC. And we know that this has a protonated hydroxyl group, formal charge plus. And then another water molecule is going to come and act as a base. So what's going to happen is that this acidic proton, whichever one, is going to be attacked by the oxygen, and then this bond is going to break, is going to go as a lone pair for the oxygen, stabilizing the positive charge, and our product is going to be CH2 here. We know the Hg group has not moved at all, HC, and then we have our hydroxyl group right there. So now we have to take out this bulky group and we have to add another hydrogen there, and we know that this is the reduction part of the mechanism, and we just write it. We can write the 2 here, and then we'll write the molecule, that molecule right there. Hg and OAC. And then this, we have sodium borohydride, and it's going to give us, it's going to take care of this group that's going to leave, and then the CH2 is going to become CH3. So our product is this. OH and CH3 instead of the CH2. And this is the same as that.